Section 6.6, the fundamental theorem of algebra. Our objective is to use the fundamental theorem of algebra in solving polynomial equations with complex roots. We have solved polynomial equations and found that their roots have been integers, rational numbers, and irrational numbers, and imaginary numbers. But can all polynomial equations be solved using complex numbers? In 1799, the German mathematician Carl Friedrich Gauss proved that the answer to this question is yes. His theorem is called the fundamental theorem of algebra, and of course it must be a big theorem if it's called the fundamental theorem of algebra, which is what we're learning. Every problem, every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. And remember, every number can be written as a complex number in the form of a plus bi, where bi is the imaginary part and a is the real part. So we can say this in a different way. So including imaginary roots and multiple roots, an nth degree polynomial equation has exactly n roots, or remember the same thing, roots is the same thing as just saying 0. Or it's also the same thing as saying the x-intercepts. So the related polynomial function has exactly n zeros. We can factor a polynomial degree n into n linear factors. So this is what I was saying before, that whatever the degree of your equation is, that is how many zeros you should be able to find, whether they're real, imaginary, or irrational or rational. Now, for the equation that we're given here, we want to find the number of complex roots, the possible number of imaginary and real roots, and the possible rational roots. So complex roots means we want to figure out how many answers are we going to have for this equation. So in order to do that, we have to look at the degree. So when you're doing these problems, make sure your equation is in standard form, which our equation is, and then the degree is the one with the highest term. So this term is degree 3, this term is degree 2, 1, and 0. So the highest degree means that this polynomial is a degree of 3, and remember degree 3, the name for that is cubic. So the number of complex roots would then be 3 because the degree is 3. Then it says to find the possible number of an imaginary roots and the possible number of real roots. Now, when we're finding the possible number, we're really looking for the combinations. So possible number means to find combinations of real and imaginary solutions you can have. So again, we're finding the combinations of real and imaginary answers that we can have for the given equation. I'm going to make this a little bit small. Okay, I just moved that so that I can write over here. Now, the way that you want to find the possible number of imaginary roots and real roots is I like to make a table to help me. So I is going to stand for, of course, imaginary. And then R stands for real numbers. And T is going to stand for the total. So usually I just write IRT. Now, remember that imaginary roots have to come in pairs because of the imaginary root theorem. So we can't have odd imaginary roots. The way that you find the possible number of imaginary roots is you look at the degree of your equation. If it is odd, then it's going to be one less than the degree. Combinations of even numbers that go up to that. And if it's even, it is going to be combinations starting from 0 up to the degree that's even. So in this case, if we have degree 3, then I know that I can have 0 imaginary answers, and I can possibly have 2 imaginary answers. Now, I can't have 1 because, remember, imaginary roots have to come in pairs. So if I have 1 imaginary root, that wouldn't work. So now we need to come up with the possible number of real roots that we can have. Well, if we have 0 imaginary roots, then how many real roots would we have to have? Well, if this is a polynomial of degree 3, we would have to have 3 answers. So that means if I have 0 imaginary roots, then I would have 3 real roots. So then the total number of zeros that I would have would be 3. If I have 2 imaginary answers, then that means I have to have 1 real answer because the total between the two has to add up to the degree, which in this case is 3. So the possible number of imaginary roots would then be 0 and 2, and the possible number of real roots would be 1 and 3, or if you want to write 3 and 1, it doesn't really matter which way you write it. So those are the possibilities. Now, the next thing that we want to do is we want to find the possible rational roots. So we've done the possible rational roots before. Remember, the possible rational roots is your p over your q. So p, remember, is factors of the constant, which is 6, and the leading coefficient is your q, which in this case is 1. It's not written. So p over q is going to be plus or minus factors of 6. So 1, 2, 3, and 6 are factors, all over my constant factors, which is just 1. So then if I write this out, I have plus or minus 1, 2, 3, and 6. So plus or minus 1, 2, 3, and 6. Now, it didn't ask me to find the actual roots of this equation, so we don't have to do anything else. That's it. So let's go ahead and look at number 2. So for this equation, again, we're doing the same thing. If I want to find the number of complex roots, I have to figure out the degree. Well, this is already in standard form, so the degree of this equation is, in this case, 4. So then I know that this equation has to have 4 answers or 4 complex roots, whether they're real or imaginary. Now it says to find the possible number of imaginary roots and real roots. So I'm going to make my table I, R, T. Remember, I stands for imaginary, R stands for real, and T stands for the total number of zeros I have to have. So if this is a degree of 4, then I know I can have combinations for imaginary roots would start with 0, and then it would be 2, and then it would go up to the degree, which is 4. Remember, I can't have 1 or 3 because those are odd, and they wouldn't be a pair then if I had that for my imaginary answers. Now, because of this, I can figure out how many real I would have if I have that combination of imaginary. So I know my total for each of them has to be a total of 4 because the complex roots is 4 because the degree is 4. So if I have no imaginary answers, then that means I have to have 4 real. If I have 2 imaginary answers, that means I would have to have 2 real, because 2 plus 2 would be 4 answers then. If I have 4 imaginary, then I would have no real. So my possible number of roots for imaginary are even, 0, 2, and 4. And your answers for imaginary will always be even because they come in pairs. So if it's like the last one, it's 1 less than the degree. If it's odd, if it's even, it goes up to the degree, the even pairs. Now the possible number of real roots would then, if you want to write backwards, 4, 2, and 0, because it goes with the ones above it. Notice that if it's an odd degree, you're going to have odd possible combinations. If it's even, you're going to have even possible combinations. So now we need the possible rational roots. So that's, again, my p over q. So my p in this case would be my constant, which is 1, and my leading coefficient is my q, which is 1. So plus or minus 1 over 1 is just plus or minus 1. And that would be my answer. Why don't you guys see if you can pause the video and do number 3 on your own, and then unpause it, and we'll do it together. So this polynomial is in standard form, so the degree is 7, so that's how many complex roots I have to have. So for my table IRT, so since this is degree 7, I can have 0, 2, 4, or 6 possible answers. I can't do 8 because 8 is above the degree of my equation, so I can't have 8 answers. Then my real combinations, I know my total for each of them has to be 7. So if I have 0 imaginary, I have to have 7 real. If I have 2 imaginary, that means that I have to have 5 real. If I have 4 imaginary, that means I have to have 3, and 6 would be 1. So my possible imaginary roots combinations would be 0, 2, 4, or 6, and then my possible real root combinations would be 7, 5, 3, or 1. So my possible rational roots, again, my p over the q. My constant is 19, so plus or minus factors of 19 are just 1 and 19. Over factors of my leading coefficient, which is just 1. So just 1. So my possible rational roots would be plus or minus 1 and plus or minus 19. If it asked me to find the actual rational roots, I would plug those into my equation and then figure out which ones worked. So now for number 3, it says find all the zeros of the function that's given. So this is like what we did before. If I want to find all the zeros of this function, then I need to figure out my possible rational roots, my p over q. So p over q would be plus or minus, and before I do that, if I look at the degree is 3, which means I should have 3 solutions to this equation when I'm finished. So my constant is 2, so plus or minus 1, factors of 2 are 1 and 2, over my leading coefficient, which is 1. So then I'm doing plus or minus 1 and plus or minus 2. Now the second part, remember, so that's the first step. The second part is to figure out your actual rational roots, which ones work when you plug them into your equation. So if you go to my calculator, and plug in the equation x cubed plus x squared minus x plus 2, you guys could probably do this on your own and then unpause it to check your answer because we've done this before. So then when I do that, need to find my zeros. If I hit my graph, just to look at the nice window, notice that I'm only seeing 1 0, but I need to make sure I'm looking at a window that's showing all my zeros. So I have from solutions that could be possibly my answers to 19. So I'm going to change my x minimum to negative 20 and my x maximum to 20. And this by ones. So if I hit graph, I just want to make sure that I'm not missing any of my possible rational roots because it was plus or minus 1 and plus or minus, I'm looking at the last problem. So plus or minus 1 and plus or minus 2, so I didn't need to go that far. So I'm just going to go back to Zoom 6. So I see only 1 real solution, so that means that my other 2 are probably imaginary. If I look at this, I can tell it looks like my solution is at negative 2, so I'm going to just check second trace value negative 2, enter, and I get 0, so I know it works. If you want to check the other ones, you can, but they're not going to work. So over here, my actual rational root would be x equals negative 2. Now that I have my actual rational root, in order to find the other zeros, I have to now use synthetic division. So that's my third step, remember? So I use my 0 that I just found, so negative 2 goes in the box. We have 1, 1, negative 1, negative 2. Bring down this term. 1 times negative 2 is negative 2. Negative 2 plus 1 is negative 1. And then this would be 2. 2 negative 1 gives me 1. And 1 times negative 2, we're missing something. Oh, this should have been plus. Sorry, I didn't see that sign because of this right here. So 2, negative 2. So I knew I did that wrong because I couldn't see that sign right there, which is plus 2. So that I put in wrong, so that was a positive 2. And I knew that was wrong because I should always get a remainder of 0 when I do my synthetic division. So now I have my synthetic division. I can write my equation. So for this equation, I have x squared minus x plus 1 equals 0. This right here is quadratic, so in order to find the other 2 solutions, I need to use the quadratic formula. I know that I'm not going to be able to factor it because I know my other 2 solutions are imaginary. So when I do this, my a value is 1, my b is negative 1, my c is equal to 1. So remember the quadratic formula, x equals negative b plus or minus the square root, b squared minus 4ac all over 2a. So when I plug this in, x is equal to negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times 1 over 2 times 1. And if I simplify, x is equal to 1 plus or minus the square root of -3 over 2. And then, of course, we don't like negatives underneath the radical, so it would be 1 plus or minus I root 3 over 2. So then now I have all my solutions, which I'm just going to write up top here. So x is equal to -2 is one of my solutions. 1 plus I root 3 over 2 and 1 minus I root 3 over 2 give me my other two solutions for a total of 3, so I know I'm done with the equation. So let's go ahead and look at the last one. It says, find all the zeros of the function, then write the equation as the product of linear factors. So if I want to find all of the zeros, I need to figure out which ones are going to work. So for this one, again, you have to find your P over Q. So I would suggest that you guys maybe try to see if you can do this one on your own and then unpause it and see if you get the same thing. So for this one, my P over Q, so factors of my constant are factors of 12. So what are factors of 12? We have our plus or minus in front. So 1, 2, 3, 4, 6, and 12 are factors of 12. And then my leading coefficient is 9, so factors of 9 are 1, 3, and 9. So if I want to write this out, each number in my numerator has to go over my denominator. So plus or minus 1, I'm going to just do this, 1, 2, 3, 4, 6, and 12, because that was all over 1. Now I have to take each of these numbers that I have here and put it over 3. So when I write that out, I would get 1 over 3, so 1/3, and then 2/3, and then 3/3 is 1, so I don't need to write again. Then I have 4/3. And then 6/3, which is 2, so I don't need to write that again, and 12/3, which would just give me 4, so I don't need to write that one again. Now that I've done that, I need to take all those numbers that I just did, and so all of these numbers have to go over now 9. So 1 over 9, and then I have 2 over 9, and then I have 3 over 9, which is just 1/3. We already have 1/3 right here, so I don't need to write it again. And then 4 over 9. So the next one I have is 6 over 9, and 6 over 9 reduces into 2/3, and I already got that one, so I don't need to rewrite it again. And then 12 over 9, which again also reduces into 4/3, so we already have that. So then those would be all my possible rational roots. And then the next thing that I need to do is figure out my actual rational roots. So to figure out your actual rational roots, you need to plug this into your calculator, y equals, and figure out which ones work. After you do that, we're going to stop for that, and like I said, see if you can finish the rest of this on your own, and then come back and we'll do the answer. So when I go to my calculator, y equals, let me clear this out, I have 9x to the 4th plus 3x to the 3rd minus 30x squared plus 6x and then plus 12. So if I hit graph, I can see 1, 2 zeros on my graph. So if I look at this, my zeros are on the negative side, and my highest window that I should be looking at is from -12 to 12, because my highest and lowest possible root is plus or minus 12. So I'm going to change that just to make sure, which I don't see anything over there. So I'm actually going to change my window and maybe in closer. So I'm going to do -5 to 5 because I don't really need it that far away. So when I do that, I can see I have zeros here, here, and something going on there. So I'm going to try I'm going to do my table. So second window, I have right here on auto, from auto to ask. So if I go to my table, I'm going to try my numbers that I had. So I had 1, -1. So 1 works. If I do -1, that does not work. 2, -2. 3, -3. And then I had 2/3, -2/3. And I would keep on going and finding all these numbers. So I know that none of the other numbers are going to work, so to save time, I know that my zeros are going to be x equals 1 and -2. So now that I have my actual rational roots, this is when I do my synthetic division. It doesn't matter which one you pick first, you're going to end up with the same answer in the end. So I'm just going to do synthetic division with 1 first. And make sure your polynomial is in standard form, and if you're missing any zero placeholders, make sure to write those in. So 9 times 1 is 9. And then remember, you add these together. So 12. 12 times 1 is 12. And then this would be -18. So I get my remainder of 0. And then remember, when you have another 0, you have to do synthetic division again with that second 0. So if you wanted to write this out with the x's, you can, but it's not necessary. Remember, you can just put your 0 right here and do your synthetic division. So when I do that, I end up with 9 times -2, which is -18. It's -6. And again, notice my remainder of 0. So since I did synthetic division twice, and this is a polynomial to degree 4, these x's right here, this would be x cubed, x squared, x. So this one is going to be x squared minus 6x plus minus 6. Now to find the remaining zeros that I have, I can use the quadratic formula. So my a is 9, my b is -6, my c is -6. Oops. And when I do my quadratic formula, oops, I put my a value there. -6 would be +6. Oh my goodness, having all kinds of problems. Okay, so when I simplify this, I get x is equal to 6 plus or minus the square root of 252 over 18. And then 252 is going to simplify, so I get 6 plus or minus 6 root 7 over 18. I can factor out that 6 in the numerator. And 6 goes into 18 3 times. So x equals 1 plus or minus root 7 over 3. So those are 2 of my answers, and also 1 and -2 were the other zeros. So these are all my zeros of the equation. Okay, so I made it a little bit smaller so we can see it on the same screen. So now that I found my zeros, remember the original question says find all the zeros, which we did, then write the equation as a product of linear factors. So linear means that your x's shall all be degree 1. So what you do to do that is you take your zeros, and remember it's always x minus your 0, so we have x minus 1, and then x minus -2 would be +2, and then remember we have 2 zeros right here, so we have x minus 1 plus root 7 over 3, and x minus 1 minus root 7 over 3. So we can simplify that. This would be 1 minus root 7 over 3 if we take out the parentheses, and x minus 1 plus root 7 over 3. So this would be my product of linear factors, and then again my zeros are right here. So just bring this with you to class, and we're going to do more practice in class.